Hey, good morning, pre-calc. CCTI, Mr. Pashar here once again. I hope everybody's doing well. Not too sunny out today, kind of gloomy. So a perfect day to do some mathematics. Yes, I did shave my beard and mustache. It's gone. Maybe it'll return in the fall, who knows. But I hope everybody's doing well. I do miss you guys. I miss being in the classroom, especially for this stuff, trigonometry. This is definitely one of the topics I think, other than probably calculus, that you really need to be in the classroom for. So I'm hoping that you did okay with Khan Academy. You've been doing the work, but the assignment that I gave you yesterday now comes back into the textbook. So today I'm going to go over a couple of things on the board here with you and show you how to do some of your homework problems. Just want you to know, whatever you learn in trig this year, especially the seniors that are going to be graduating, the juniors that will be going on the calc, and even the juniors that will not be going on the calc, but going into prob and stat next year. We're only learning the tip of the iceberg, and there's so much more I really would like to teach you about trig. We just don't have the time, and because of the situation we're in, it makes it a little more difficult. So I've been trying to use Khan Academy to help fill the gaps for you with this topic. I understand it's a little bit difficult to do online. Believe me, I know. I'm not a big fan of this, but this is the situation we're kind of dealt with at this time. So what I'm going to do is I'm going to go back and review a couple of small things with you. The two special triangles. I'm going to talk about radians with you briefly, and then I'm going to move into reference angles. Because reference angles are a big deal, actually. They help us to take everything back into perspective of the 30, 60, 90 triangle, 45, 45, 90 triangle. They help us to do a majority of trig stuff, which is nice. Can't do everything, but it'll do a lot for us. You would rather want to know the value of sine at 30 degrees versus sine of 210 degrees. Nobody memorizes sine of 210 degrees unless you have too much time on your hands. So let's review a couple things here. We'll start out with the first special triangle we talked about, which was a 30, 60, 90. So I'm going to put the 30 down here. I'm going to put the 60 up here, and of course that's 90. So in a 30, 60, 90 triangle, the leg opposite the 30 degrees, if you remember what that is, that's going to be 1. The leg opposite 60 degrees is root 3, and the long side is 2. Please keep in mind this triangle especially is not drawn to scale. It's just used as reference, okay? So we have this mark up here, and the importance of understanding at least the 3 trig functions from this will help you to do a lot. For example, if we want sine of 30 degrees, remember sine's ratio is always the opposite over the hypotenuse. So opposite the 30 is 1, and then the hypotenuse is 2. So sine of 30 degrees is 1/2. You have also seen sine of pi over 6 is 1/2, because pi over 6 is the radian equivalent of 30 degrees, which we'll talk about shortly. Cosine of 30 degrees. Well, cosine of 30 degrees, that's going to be the adjacent side over the hypotenuse, so that's root 3 over 2. And then tangent of 30 degrees, that is your y over x, right, or your opposite over adjacent. So that's 1 over root 3, which is a fine answer, but we can rationalize this to root 3 over 3. More times than not, you'll see it written this way, rationalized. Especially in our textbook, they rationalize the answers when you check in the back. And from these 3, you get the other 3 trig functions for free. So sine's reciprocal is cosecant. So cosecant of 30 degrees is going to be 2 over 1, or just 2. Secant of 30 degrees. Don't you just hate when that happens? Secant of 30 degrees is going to be 2 over root 3, or rationalize 2 root 3 over 3. And cotangent of 30 degrees is going to be root 3 over 1, or just root 3. So you see, you get those 3 trig functions for free. That's the 30, 60, 90 triangle. Okay? So this brings up a good question. So for example, we know that sine of 30 degrees is 1/2, but say we wanted to figure out what is sine of 210 degrees. what does that equal, right? Sine of 210 degrees. And unless you have a table in front of you with all the values, like your book would possibly have, you may be kind of stumped. And if you certainly don't have a calculator, you're kind of screwed then anyway. So, and by the way, the downside with a calculator is a lot of times they just give these things in decimals, so you may miss out on the radicals. But anyway, this brings us to a topic which we call reference angles. How do we find a reference angle? Because if we could find a reference, then we could actually apply it to what we know here. So this is where our discussion begins today, where we begin moving past quadrant 1. So all the triangles you worked with have been quadrant 1 triangles, but what happens if the triangle takes place in quadrant 2, 3, or 4? I'll show you the easy ways to get around that. But let's kind of think about where this is located. So here's your coordinate plane. So sine of 210 degrees. So as you know, your angle starts in its terminal position here on the x-axis, so that would be considered 0 degrees. If you rotate up to here, this is 90 degrees. If you continue to rotate, so this would be 90. If you continue to rotate, this would be 180 degrees, right? So there's 0, 90, 180. If you rotate all the way down here, this is 270. And if you continue to rotate back up to here, this is 360 degrees. So 210, if we were going to draw that angle, would be somewhere in here. So angle theta would represent 210 degrees, and we would technically draw a right triangle up to the x-axis. So now our triangle would be in quadrant 3, and what that does is it messes with the signs. See, everything's nice and positive now, but when you go down another quadrant, some things are going to be positive, some things are going to be negative. Reference angles tells you the trig function, but your brain has to tell you the sign. So here's how we figure what the reference is. If we have a 210 degree angle, the angle on the inside, right here, the actual angle inside the triangle, that's what we call theta prime. And theta prime is your reference. If your theta prime happens to be down in quadrant 3, you go up to the nearest quadrantal angle. These angles here, 0, 90, 180, 270, 360, those are what we call quadrantal angles. So what we do is we go up to the nearest quadrantal angle, which would be 180. So you're going to find theta prime, you're going to take 210 degrees minus 180 degrees, and that gives you 30 degrees. So in other words, if you know what sine of 30 degrees is, you know what sine of 210 degrees is. So sine of 210 degrees is going to be a 1/2. And the only thing we got to do now is figure out what the sine is going to be. Well, down in quadrant number 3, sine is negative. So sine of 210 degrees is negative 1/2, not positive 1/2. How do you know the signs? Well, here's an easy trick for you. Let me erase some of this stuff. Here's an easy trick. And if you read the book, you would have seen this. If you think of the coordinate plane, think of this rhyme. All students take calculus. All students take calculus. This is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So, in quadrant 1, all trig functions are positive. In quadrant number 2, sine and cosecant are positive. In quadrant 3, tangent and cotangent are positive. In quadrant 4, cosine and secant are positive. So if you remember that jingle, all students take calculus, all trig functions positive, sine and its reciprocal are positive, t, tangent, and cotangent are positive, that's the reciprocal, and down in quadrant 4, cosine and its reciprocal secant are positive. So that's why down here, sine of 210 is going to be a negative number. Okay? So that's how that works. Let's look at something else. How about we want to figure out maybe cosine of 330 degrees. Okay, that's a rather large number, right? 330 degrees. So let's try to figure out where this angle will be located. So 330 degrees would be somewhere here, right? So theta is 330 degrees. And then this, when you draw this triangle upwards, right? This angle on the inside is theta prime. That's your reference. So we want to figure out what the reference is going to be here if we wanted to figure out cosine of 330. So we draw our perpendicular line up to the nearest quadrantal angle, which is 360. So we're going to find theta prime. It's going to be 360 minus 330, which is going to be 30 degrees. So once again, if we know what cosine of 30 degrees is, we'll be able to find out what cosine of 330 degrees is. So cosine of 30 degrees, if you remember from your 30, 60, 90 triangle, that's going to be your adjacent side over your hypotenuse. So that's going to be root 3 over 2, okay? But now, if we want cosine of 330 degrees, it's going to be root 3 over 2, but we have to figure out what the sine is going to be. So what's the sine going to be? Well, you're down in quadrant 4, and in quadrant 4, the trig functions that are positive are cosine and secant. Therefore, this thing is going to be positive. And that's how you figure it out. Like I said, the special triangles will take care of most of the things you need to do. We also had another special triangle, which I never had an easy time drawing this because I can never get it to scale. And I probably won't get it to scale here either. But we have what we call a 45, 45, 90 triangle. So on the 45, 45, 90, the legs are both worth 1, and the long side is worth 2. And we can play the same exact game that we did over here with the 45, 45, 90 triangle. So that's another triangle that you need to commit to memory. Okay, so that brings us to the next idea, which you should have done on Khan Academy, which is the idea of radians. In trigonometry, most of the time we actually use radian measure other than the degree measure. Radians are more popular. And there's actually another unit of measure called gradians, G-R-A-D. We usually don't use those, but that's another measurement as well. But we use radians. And the thing with radians is they don't have a unit symbol. So you know, like in chemistry, for example, everything is a game of units, as you hear, right? So you have moles, MOL, grams, G, ATM for atmosphere, but radians doesn't have anything. So here's how we do it. So if you want to go from degrees to radians, what we do is we're going to go ahead and we're going to multiply the degrees by pi over 180 degrees. And the reason why we do that is, as you know, the units will cancel, so the degrees will cancel out with the degrees, and you'll be left with the pi on the top. So, for example, say we have, what do I have here, 270 degrees. We want to figure out how many 270 degrees are in terms of radians. So what we're going to do is we're going to multiply that by pi over 180. So you see what happens. The degrees will cancel out. So you have 270 pi over 180. And then all you have to do is simplify 270 over 180. Leave the pi go. Don't make an approximation. Keep the pi. Maybe it's apple or blueberry or my favorite, which is pumpkin. 270 over 180 is 3 pi over 2 radians. And again, we don't write typically radians or RAD after. We just leave it as this because it's universally accepted in the math community that when we see something like that, it must be radians. Another popular one is 45 degrees. So 45 degrees in terms of radians will multiply by pi over 180 degrees. The degrees knock out once again. So you have 45 pi over 180. And when you reduce 45 over 180, that's going to give you just pi over 4. So many of these you're going to see over and over again. They pop up all the time in trig. Very popular. I would also like to give a shout out while we're talking about this stuff. Since this is Teacher Appreciation Week and yesterday was Teacher Appreciation Day, do want to give a shout out to a few teachers in the math world that are very good teachers. For me, trigonometry, Mrs. Demera at Hazelton Area High School. I had her actually for trigonometry and the college algebra. And I wished her a happy Teacher Appreciation Day yesterday. Some other notable math teachers, Mr. Hawes, Mr. Konar, Mr. Ravina, Mr. Stelmach, Mrs. Fiola. She had a big impact on me becoming a math teacher. So Mrs. Fiola, calculus teacher at Hazelton Area High School. I wished her a very happy Teacher Appreciation Day yesterday. Who else? There's a long list of teachers. Mrs. Hudak, my French teacher. Of all the teachers I had the most patience you'll ever see. Mr. Moss, my chemistry teacher from high school, he gave me a very good, solid background in general chemistry that helped me big time for college. So I talked to him yesterday. But there's a lot of teachers, So even for you guys in high school, it's not a bad idea. Take the time to thank one of your teachers from the past that had an impact on you. As I always say, as a side note, and maybe you heard me say this before in class, teaching is a very thankless profession. None of us that become teachers ever go into a profession wanting recognition, wanting praise. We know we're not going to get it. We know sometimes we are enemies of the taxpayers, oh, teachers get off in the summer, blah, blah, blah. You've been hearing that for years. There's a lot to our job. We do a lot behind the scenes that you guys don't know. We just don't, oftentimes I think you guys just see us as, we come up to the front of the class, teach stuff at the board, put your grades in a computer. There's much more that goes on. So take the time to thank a teacher if you can. Okay, now how about, this is how we go from degrees to radians. Now, it's also important to go from radians to degrees, especially when you're just learning trigonometry. You're going to see things that in radians that you may not register in your brain, and we like to convert them to degrees so we get a better idea. The perfect example is what we did over here before, the reference angles. It's easier to put radians into degrees, find the reference angle, and if we have to go backwards, so be it. It's a little bit easier. So, for example, if we want to go from radians to degrees, what do we want to do? Well, we're going to multiply by 180 degrees over pi. We want the degrees on top so we can knock out the radian idea, and we want to put the pi on the bottom so it knocks the pi out consequently for most of the cases. Not all the time. For example, I may give you 2.2 radians, and we have to convert that to degrees, and we'll still have the pi remaining. And that's when we'll probably want to get an approximation, because usually when we write things in terms of degrees, we don't say like 3.2 pi degrees, right? We want a decimal approximation. So here's an example. How about if we have 3 pi over 2? So say we're working and we need a reference angle or something, and we got to take 3 pi over 2. We want to figure out what this is in terms of degrees. Well, we're going to multiply that by 180 degrees over pi. So you see what happens, the pi's get knocked out, and then we could divide here if we wish. So what this is going to be is 270 degrees. You see that? No pi symbols left at all. Okay. So that's how that works. That's how you go from radians to degrees. Okay, I'd like to just take the time to look at an example here of some things. So what we're going to do is we're going to look at a couple of things here. And for example, if we want to find some things like this, so we want to find sine of 5 pi over 3. So right away, it's kind of an issue because it's in radians first of all, so you're not as familiar yet with radians. And we got to find the trig value. So where is 5 pi over 3 located? So this is a good idea to probably convert the 5 pi over 3 into radians, the degrees, find a reference, use that special 30, 60, 90 or 45, 45, 90 triangle to help find the value. So let's go ahead and do that. So we'll take the 5 pi over 3, and let's find out what this is in terms of degrees. So that's 180 degrees over pi, okay? So 5 pi over 3 times 180 degrees over pi. The pi's cancel out. Okay, let's see what we get. When we do that, mathematics, you're going to get 300 degrees. So essentially what the question is stating, the original question is stating, what is sine of 300 degrees? Well, who the hell knows? Unless you're a walking table, you're probably not going to know what this is right away. So let's go and figure it out. Let's find the reference. So where would 300 degrees be? Well, that would be somewhere here, right? So this would be 300 degrees. So we draw our triangle. Theta prime is our reference inside. So what we're going to have here is find theta prime. Don't you just hate when that happens? Well, I'd rather that than the black. Look, my hand's full of white from the chalk, but I'd rather that than the black from the markers. I hate the whiteboard, as you know. So anyway, this is going to be 360 degrees minus 300 degrees. So theta prime is 60 degrees. So that is our reference. So if we could figure out what sine of 60 degrees is, and couple that with where this is located, quadrant 4, we'll know what this is, okay? So sine of 60 degrees. If you have to draw your right triangle, I'm going to put the 30 here. There's the 60. So across from the 30 is 1, across from the 60 is root 3, and across from the 90 degrees is 2. So what is sine of 60? Well, sine of 60 is going to be the opposite over the hypotenuse. So that's root 3 over 2. So sine of 60 is root 3 over 2. So then sine of 300 is also going to be a root 3 over 2, but we just got to check out what the sine is going to be. Okay, so you see, that's how important the reference angle is. So sine of 300 is also root 3 over 2, but where is that located? Well, 300 is down here in quadrant 4. And what things are positive in quadrant 4? Well, all students take calculus. So in quadrant 4, cosine and secant are positive. That means sine has to be negative. So therefore, sine of 300 degrees is negative root 3 over 2. Okay? Okay? So, why don't I give you guys one to try here? How about you try this one? Find cosine of 7 pi over 6. So find cosine of 7 pi over 6. I'll let you guys work on that. and we'll come back and see how you did. Okay, so let's see. Okay, so first step is, let's see, well, what exactly is 7 pi over 6 in terms of degrees? Maybe that will help us out. So we're going to multiply 7 pi over 6 by 180 degrees over pi. Okay, the pi's will knock out, and when you're done, you should get 210 degrees. So the question now is, what is cosine of 210 degrees equal to? Well, we may not know readily what it is, so let's find the reference angle. So the reference angle here, 210 degrees, if you think about where that is, that's somewhere here. So what we're going to do is theta prime is always your reference angle. So theta prime is going to be 210 minus 180, right? And what is 210 minus 180? Well, that's 30. So theta prime is 30. So let's figure out what is cosine of 30 degrees. Well, if you know your 30, 60, 90 triangle, it's easy. It's going to be root 3 over 2. So cosine of 30 is root 3 over 2, which means cosine of 210 degrees, which is the same thing as saying cosine of 7 pi over 6, is also going to be a root 3 over 2. We just got to check out the sign. That degree, 210, that is over in quadrant 2. Now what's positive in quadrant 3, excuse me, 1, 2, 3, can't count. What is positive over in quadrant 3? All students take calculus T. So tangent and cotangent are positive, meaning everything else is negative. So therefore, cosine of 7 pi over 6 is negative root 3 over 2. You'll see some of these exercises in the homework that was just assigned to you yesterday. Okay? So I hope that helps you a little bit with that. And again, you can play the game for all the other trig functions as well. So if you noticed in all of these examples, what we've been doing is taking the trig into the other parts of the coordinate plane, not just staying in quadrant 1 where it's boring all the time. So what I'm going to show you next is a new definition on how we define trig functions. And this is what was in your book. We define the hypotenuse as x squared plus y squared, or in other words, the distance from the point up to the axis, right? That distance. So r is going to be x squared plus y squared. And picturally speaking, right, if you have an angle drawn like this, here's theta. This point on it is xy. So the point on the terminal side of the angle is xy. And then, of course, this is your r. So x is this guy, y is that guy. That point xy was something familiar in terms of the unit circle, if you remember doing it on Khan Academy. So that gets us into another realm, but we're not going to get too far ahead of ourselves here. So when you have this type of setup, we can rewrite our trig ratios in another way. So we could say that sine of theta is y over r. So there's the y over the r. Cosine theta is x over r. And tangent of theta is going to be y over x, provided x isn't 0. Because if x is 0, then it's undefined. So that means cosecant of theta is r over y, provided y isn't 0. Secant of theta is r over x, provided x isn't 0. And cotangent of theta is x over y, provided y isn't 0 as well, okay? So this is a new way of defining it, our trig functions, right? And I'll show you a couple of examples on how this works. And a lot of this can be done very quickly. For example, I'll show you. So here's an example. We could say when x is 3 and y is 2, r is going to be root 13. So sine of theta, for example, is y over r, which is going to be 2 over root 13. Or you can write that as 2 root 13 over 13. Okay? So that's what happens there. So I'm going to give you an example on how this works, and then I'll show you one other type of problem that you will encounter. There's two ways to do it, but I'm going to show you the easier of the two ways, because the alternate way is a little more confusing. The way I'll show you is based on the stuff we've been doing, and as long as you know what quadrant, what trig function is positive, then it makes this thing a lot easier. So here's an example. We're going to determine all 6 trig functions. Given the point, and the point is -3, 4. So this is a terminal point on the side of an angle, so this is where the angle is resting. Okay, so what we're going to do is look at the stuff that we have. The ingredients essentially is x is -3, y equals 4, and r we don't know. Okay, remember what r is. R is that distance. So r is given by the formula x squared plus y squared. Okay, again, if you think about it in the triangle, there's your x, there's your y, this is the r. Okay, it's the distance essentially between the x and the y. So why don't we draw the picture just to get a bearing on what's going on. I think you'll agree that -3, 4 would be somewhere over here. So that means we're rotating an angle over here to this point, right? And it would rest here. So this angle itself is theta. But what we really are doing is we're looking for this triangle here. So this is really theta prime on the inside. But we're looking to still find theta. But what we're actually using is theta prime essentially in a way behind the scenes. So this isn't actually too bad because, as you know, this right triangle, here's your x, there's your y, and there's your r, right? So, you know, if you're looking for sine, that's the opposite over hypotenuse, so on and so forth. So what we're going to do is find r, and that's the only numerical piece we need, and then we'll be able to go ahead and figure out the trig function based on those definitions. So what is r going to be? Well, r is the square root of x squared plus y squared. X is -3, so we got -3 squared plus y squared, which is 4 squared. So we're going to get 9 plus 16. That's the square root of 25, which is 5. So the distance here in this problem would be 5. So there's your -3, there's your 4, and technically we say -3 in absolute value because a triangle can't have a negative distance for legs, but technically it is in a way -3 because of the point. But your long side can never be negative because that's your positive distance, where we call it a modulus. in any case, now we could go ahead and do this. We have all pieces of information. So now we got this. So sine of theta is y over r. So you don't even, if this bothers you, you don't even need this crap, because once you find r, you're just plugging in these values here. That's the easy thing about it. So if sine of theta is given by y over r, so y is 4, r is 5. So the ratio is 4/5. And this should make sense to you because over in quadrant 2, sine and cosecant are positive. Isn't this thing positive? See, it's no coincidence. How about cosine of theta? That cosine of theta is x over r. X is -3, r is 5. So your answer is -3/5. That should make sense to you because cosine is not positive over here in quadrant number 2, right? So it has to be negative. And then tangent of theta is y over x. We call tangent the slope function for a reason. So y over x, that's 4 over -3. And once again, that should make sense to you as well because of the fact that tangent is not positive over here. Okay? And I gotta get more chalk. I'm going through chalk pretty quickly. Now let's finish this out. Once you have these three, the other three are pretty easy to grab, right? Because they're just reciprocals. So remember, with the reciprocals, the sign goes with it. Doesn't matter where you put the sign as long as it's with the ratio. So cosecant of theta is going to be 5/4. Secant of theta is going to be -5/3. And cotangent of theta is going to be -3/4. We got them just like that because they're just the flip-flops of sine, cosine, and tangent, respectively. Okay? So that wasn't all that bad. So if you could do one example, then you could certainly do others. It's not too bad. I'm going to show you another example that will pop up based on this stuff that isn't so bad either, once you understand. And again, please, make sure you watch this video. Well, if you don't watch this video, you're not going to hear me saying to watch this video. But in any case, if you watch this, also make sure you read your textbook so you can see the examples too. But this is another scenario that you'll see. So here's an example. This is actually one of your homework assignment questions, so you should pay attention. This is actually number 29. We want to find secant of theta and cotangent of theta given sine of theta is -5/13. -5/13 doesn't look like a good 13. There you go. And secant of theta is less than 0. I like these problems. Brings me back to high school. I remember doing these quite vividly in Mrs. Demira's trig class. So we want to find secant of theta and cotangent of theta, and we're given sine of theta is -5/13. Can you see that? Maybe I'll turn this a little bit, Hannah. There you go. -5/13 is sine, and we're given that secant of theta is less than 0. So this is a very important part of the problem. This tells us that secant is negative. So we have to figure out essentially, if sine is negative and secant is negative, where are we in the coordinate plane? So let's kind of draw a coordinate plane here. So where is sine negative and secant also negative? Well, again, all students take calculus. So sine is going to be negative here and here, and secant is only negative here. So we have to be here in quadrant 3. That's where we're at, okay? So we're in quadrant 3. So now we could go ahead and take the information we have here to find secant and cotangent. So we'll go ahead and draw our triangle. I'm going to draw one that would be like we usually do. So sine of theta, I'm going to look at the absolute value. I'm not going to even contribute the minus. 5/13. So what does that mean? That's opposite over hypotenuse. So we got to find what x is in order to do this problem. So we're going to have x squared plus 5 squared is 13 squared. This is Pythagoras' theorem, right? We have two of the sides of a right triangle, so we can use Pythagoras to get the last one. So this is going to be x squared plus 25 is 169. X squared equals what? Well, we'll drag the 25 over, so this is going to be 144. So x is going to be 12. Technically, it's plus or minus 12, but however, we're looking at this in terms of absolute value, so we only want the positive one, which is 12. The other way of doing this problem would be to contribute the plus or minus and then have to kind of backtrack, but I'm trying to show you the easier way to do it. So this is 12, okay? Again, the picture is not drawn to scale. So we want to find secant of theta. Now, cosine would probably help us. So why don't we find cosine, because it's easier. Cosine is the adjacent over the hypotenuse, which is 12 over 13. So that means secant's going to be 13 over 12. You see, it's just a little trick, because most of us don't remember secant's ratio, but we know cosine's ratio. So secant of theta is 13 over 12, but now we just have to check the sign. You're down here in quadrant 3, so it's going to be negative. So we got that one. And now we need to find cotangent of theta. So let's think of tangent of theta. So tangent of theta is y over x, so that's 5 over 12. So that means that cotangent is going to be 12 over 5. And because you're down here in quadrant 3, it is positive. So cotangent of theta is going to be 12/5. Not witchcraft, just trigonometry. Not too bad. Okay. So why don't we do one more, just to make sure that we kind of have this under our belt. So how about this one? We're going to find cosine of theta and cosecant of theta. Given sine of theta is root 5 over 7. So it's root 5 over 7. And secant of theta is greater than 0. So that means secant's positive and sine is positive. So where on earth could that be? So this one isn't too hard to imagine. Both of these guys are positive, so you have to be in quadrant 1. So that means your answers are going to be positive. Okay, for all of them. So let's draw the triangle. So there's theta. Sine is what we're given, root 5 over 7. So this would be your root 5 opposite over 7, which is hypotenuse. So once again, we have to find x. So we use Pythagoras. We got x squared plus root 5 squared is 7 squared. That means we got x squared plus 5 is 49. That means we got x squared is what? 49 minus 5. That would be 44. So x is going to be the square root of 44. But we could simplify root 44, right? If we go off to the side and think about it, we could think of that as 11 times 4, so that means we got 2 root 11. So x is worth 2 root 11. That would be this guy right here, x. So let's find cosine. So cosine of theta is going to be the adjacent over the hypotenuse. So that's that 2 root 11 over 7. And we know it's positive automatically because we're in quadrant number 1. So that's good. We want to find cosecant next. So let's find sine, because sine is easy. Sine is going to be opposite over hypotenuse. So that's, that was actually given to us, right? So cosecant is going to be the flip-flop. That's going to be 7 over root 5. So 7 over root 5 is fine. You can leave it that way. But we like to usually rationalize it. So we're going to multiply the top and bottom by root 5. That's why we learned that earlier in the year. So that's going to give you 7 root 5 over 5. And that's what cosecant ratio is going to be. And that's pretty much everything that you're going to encounter in 5.3 plus stuff earlier from Khan Academy. So I hope this video helps you out a little bit here. I know learning this stuff's a little bit difficult from home. I'll give you that. But just stick with it. We're almost done. Seniors, you have less than a month to go. And underclassmen, you have also actually under a month to go because June 5th is the last day. So, I mean, we're almost there. We made it through the worst of this, I think. The virus is starting to go away. We all reached the peak. We're all going on the downhill slide. Got to get things open back up now, get back to life. But if you have any questions on this stuff, please let me know. Call, text, email, whatever you need to do. I'll be willing to help you between 11 a.m. and 1 p.m. especially. That is the office hours for us academic teachers. So until then, be safe, enjoy, and I'll catch you next time.